in English, I think. Yeah. Okay. So as we talked about last time, we will go over the notebook we pointed out last time. But before that, I don't know if everybody received the information, but we have tech meetings every first Wednesday of the month. So you're invited to participate if you want. You can write to me or Marco about that. Also, since we want to make it like more interactive and stuff, we're gonna start, you know, asking other people to present. It's nothing too, formal, but every time we're gonna point out a subject to try and read about and explore for the next meeting. We could also like choose some people who would be able to present and talk to us about said subject. We could do that for next week, not next week, in 2 weeks too. And I will tell you more about that later, but just keep that in mind. If you ever want to volunteer, you're welcome to. Other than that, I was thinking maybe we could have a zotero, like something to keep track of the paper that we read. So I don't know if that's what you use, or we could look into that. Could be interesting. And so I'm gonna share my screen so that you could see the notebook. I don't know if everybody had the chance to read it, to check it, to run it. Yeah, no, maybe. Okay, so we'll see. We'll look into it together. Uh, Teams is asking me to update.
Can you post the link in the
Right.
chat maybe?
So you should be able to see my screen. This is the notebook we talked about last time. Well, we talked about checking. This is the notebook that was introduced with the paper that we looked into with Marco last time. So the effect of data encoding on the expressive power of variational quantum machine learning models. Um, so basically, this notebook goes through what we saw in the paper and recreates the figures. If you remember, we had something like this. And basically, um, the paper was talking about the expressive power of variational quantum machine learning. And before we dive right into this paper, I want to talk to you a little bit about expressivity. Um, just gonna Yeah, what do we mean when we say the expressivity of uh, a circuit or a quantum machine learning network? We're actually talking about the ability of the quantum circuit to represent a variety of functions and transformations. So basically, what are the values that you could get, that you can cover with the said circuit? If you're ever interested in that, I have a paper that I could link to you that talks a lot about expressivity, but I'm gonna show you a figure that comes from that said paper. So expressibility and entangling capability of parameterized quantum circuits. So from this paper, there is a figure that I want to show you that I think is very interesting, which is this one right here. So when we talk about expressivity, what we're talking about is what we see here. So here we consider a single qubit circuit, and we look into its representation on the Bloch sphere. Um, so basically, what it can cover as an image. Here, when we apply by the identity gate, so when we do nothing, obviously what you can see, and I think it's a bit small, so is a single point here at the zero state. So that's all we can express with this circuit, because we're not doing anything particular. When we look into circuit A, this time we're applying a Hadamard gate, so we're putting our qubit in superposition state. Then we're applying a rotation, a Z rotation on the qubit, and we can see that what we can cover are the point here on this part of the sphere. And then when we have circuit B, we actually add a second rotation, and we have an expressibility that looks like this. If you can see, we won't go into the detail of that, but there is quite a bit of concentration on the poles here. Um, that is what this paper dives into. We won't talk about that today. And here we have an arbitrary unitary, so a perfectly arbitrary gate. And we can see that we express most point on the block sphere. That is important because if, let's say, we had taken this circuit to construct our neural network, well, obviously, we won't be very good at classifying because we're not very good at expressing the function that we want to fit, for example. So, in short, what the paper that we looked into with Marco last time um, was talking about is actually the expressive power of uh, models, um, and a way to quantify this expressive power using Fourier series. So basically, the the gist of it is that depending on the number of layers that you put and the coefficient, you're going to be able to fit functions expressed as Fourier series to up to a certain degree. And we can see that in the notebook too. So let's just that's the only thing I wanted to tell you about expressivity. And I don't know, I don't see the chat or anything. So if there are any questions, don't hesitate to talk or tell me. Oh, is that okay? Great,
I'll be looking at the
perfect.
chat, so if you need
So
the...
that's about it for expressivity. Uh, you have any question about that?
Oh, no, I was saying that I'll be looking in the
No.
chat. So if there's a question, I'll tell you.
Perfect. So I see that the link to the notebook that we're gonna look into is in the chat. Perfect. Let's dive right in. So first of all, we consider quantum machine learning models of this form. So if you remember, we have a certain transformation that we apply on a certain measurable here, observable M. Um, and M could be anything. We will see more later in what they use. So the circuit itself repeats L layers. So we have a certain number of layers that each consist of SX blocks that we can see right here in the image, which are data encoding blocks, and trainable blocks W, which are parameterized, and which is the part that we're going to train with parameters theta. Um, so the paper here, as they say, shows that a quantum model can be written as a Fourier type sum of the form here, which are here as are the coefficients up to a certain degree. And what they actually infer in the paper is that the degree is going to be correlated to the number of layers. We can see here that we have a last layer here, L plus 1, which is the trainable circuit block, another one, but this time without the encoding data following. So they use penny lane in this notebook. In our case, we will use Qiskit, which is not the same library, but we're going to talk about it a bit later, but uh, to pass from penny lane to Qiskit is I won't say easy, but quite doable. So, as they say, the goal of this demonstration is to investigate the Fourier series-like nature of quantum models. So, basically the ability to express Fourier series with quantum models and the correlation between layers. So what they start here is by importing some important libraries, and then they define a square loss function. So that's their loss. They're going to be using it to make sure their training is working properly. So basically, this is a mean square. Nothing too crazy about it. And then they talk about fitting Fourier series with serial polyrotation encoding. So if you remember, polygates are the X, Z, and Y gates that sometimes we can include the identity in polygates. So when we talk about polyrotation, we're talking about RZ rotation, ZX X rotation, Y rotation, etc. So here in the single qubit case, we have a circuit that looks like this. Basically, what we understand from this picture is they have at least two layers. These two blocks here are the first the first layer. Here is the second layer, etc. And then we expect here a layer of W here to complete the circuit. So first, we define a classical target function, basically the function that we want to fit. Here they assign the degree to 1. You can, if you want to run it yourself, change the degree. We could do that later. And yeah, scaling, coefficients, and then they define the target function as this here, which is their expression of the truncated Fourier series. And if we actually plot this, it looks like this. So as we can imagine, changing the degree here is going to be able to change the shape, the look of this function right here. So that's our target function. That's what our quantum machine learning network is going to try to fit. And some notes here about reproducing the figures in the paper. If you want to do that on your end, those are the parameters that you need to set. So then we go on to define the serial quantum model. So here we have this line here, which calls QML.device. This is proper to Penny Lane, and every time you see something like this, a function or anything, there is a documentation associated with it. So if we go look into what quantum device actually does, um, basically returns an instance, which we're gonna use to uh, create our quantum circuits. So here, the number of wires is actually here initiated to 1 because we are actually looking into um, one qubit circuits. So wires are actually these lines here. So basically the number of qubits. All right. So they create a device with a default qubit, actually, with 1 qubit. Then they define their S block, so their data encoding circuit block, which is basically one gate here, which is a Rx. So it's an X rotation. Again, if you want to look into the documentation, you can have the matrix form of this gate right here. And then they define a W block, so a trainable circuit block, by calling the ROT gate with 3 different thetas and specifying that we want this on the 0 wire, so basically on the first qubit. So here, wires is not the uh, size of the wires, but it's the index of the wire. If we go look into what QML rotation actually does, right here in the documentation, we can see that they implement Z rotation, Y rotation, and Z rotation according to the parameters that you've passed right here, which in a matrix form gives us something that looks like this. So of course, when you go into the documentation, you can have the details of the gates, so the wires that they are applied to and the parameters, etc. All right. So now that we've defined the S block and the W block, what we're going to do right now is defining the actual quantum circuit. So here with PennyLane, you do it by calling QML Q node, and then you define the quantum model. They called it a serial quantum model with a certain number of weights. So they are going through each weight except for the last one. That's what they're doing here, and creating the layers as we saw earlier. So with a W block and then followed by an S block. The reason why we're not taking the last weight is because if you remember, the last layer is only a W block. So that's what they're doing here. They're creating uh, the exact same circuit as what we saw earlier. And then they return the expectation value according to poly Z here. So the measurable, the M that was up here is defined as a Z gate. So, okay. And then you can run the following multiple times, each time sampling different weights. So each time, as you can see, if we run this cell multiple times, the weights are going to be random and generated randomly. And then if we actually use the serial quantum models with the weight for every x that we have, that is right here, and we actually plot it, we find something that looks like this. It looks quite a bit like the function that we want to fit. We could have plotted them side by side and look into that. Um, and also, they say, as they say here, no matter what weights are picked, the single qubit model for L equals 1, so for a single layer, will always be a sign function, which goes with their conclusions that they have in the paper about expressing Fourier series up to a certain degree, which is dependable of the number of gates that you applied, of poly gates. All right, so if you actually draw the circuit that they created, you find something like this. The drawing of the circuit is not really ready, so I actually I ran it on my side and I have a prettier drawing, so I could show you that. That's the exact same notebook. So we were right here. Oh no, never mind. I didn't have it any prettier. So basically what we see here is that we have a rotation with 3 parameters. So that's our W block, the first one. And then we have a X rotation, um, which is our S block, so data encoding block. And then we have our last layer right here, which is a W block again. So basically here we have one layer of our 2 blocks and then the last layer. So L equals 1. All right, let me go back right here because it's easier to read. So now if we want to fit the model to the target, we need to optimize the weights, obviously, in order to fit the ground truth. So here we define a cost function, which uses the square laws that we defined up as a first step. And we use the Adam optimizer. We could have used other optimizers. This is a default one that works well usually. And we define some batch sizes, and then we iterate through the steps, each steps, which we actually create X batches and Y batches, and we update the weights every time by using the optimizer, which is right here. And then we update our current cost and we iterate through that so that we can actually fit with the target function. So if we look here, they have printed each cost at step. You could do that. You could actually print other information if you would want to, or none to. So this is for a certain range of steps. If you run that multiple times, this cell right here, you could train the model. So uh, then here we have the prediction with the weights that we trained, and if we plot that here, depending on the number of time they ran it, you have a prediction that is quite well fitting with the target function. Um, with Actually, the target function being a sine function, it was not that hard to fit, especially since we know we can fit this kind of function with our quantum model. This is why, this is a reason why the way you construct the quantum model is important, and the expressibility is important, because imagine you didn't have a sine function here, you had something that was way more complicated. This particular quantum model wouldn't have been able to fit very well. All right, so if you have a look at the we plot the loss while training, you can see that it's actually converging to 0, which is great, and this is what we want. All right, so that's basically it. This part 2 here talks about fitting Fourier series with parallel polyrotations. So now we consider a circuit that is more than 1 qubit, and we're going to be using something that we call the ansatz. I'm going to talk about that in a second. But the idea is basically the same. We have a first W block, and then we have our encoding data block. This time around, we're gonna apply gates on multiple qubits, actually all of our qubits. And then at the end, we finish with our last layer of W block. So here they say that the ansatz is Penny-Lane's layer structure called strongly entangling layers. This is a circuit that is of the shape that we see right here. I hope it's not too small. But what that means, what an ansatz is basically is a first guess of what would be a great W block that would work, like a bit like in classical machine learning. It's our best guess, and we have a bunch of predetermined ansatz, which this one is one, and we have a bunch of other ones that you could use. So here they write from Pellin templates import strongly entangling layers. They could have imported something else. Uh, so you could link into the documentation to find other ansatz if you're interested. So here we use 3 qubits just as an example. Again, we create a QML device. This time we have 4 wires. Um, and then we create a QML nodes with, well, they define the ansatz with weights. Basically, here they call it ansatz. We could have called it W. It's the same idea here. Um, and we use the strongly entangling layers, so the circuits that we saw right up there with a certain number of weights, and we return the expectation value um, of this whole thing. Here, if we draw the ansatz, we have it right here. So rotations on the 3 qubits, followed by CX gates. If you remember, those are controlled X. So this X right here is going to be applied only if this qubit is 1. Same from here, and same for here. So the dot is the control qubits, and the X is the target qubit. And then it's followed by other rotation on the 3 qubits again, and then another layer of CX gates. So when you define the actual quantum model that we're going to use for training, Here they call it again S. So S is the data encoding circuits. This time around, we don't have a single Rx here because we iterate through all of our qubits to apply the Rx gate. And then for our W gate, as I told you earlier, we use the strongly entangling layer that we defined as the ansatz. We could have used another one. So for our model, we have a W uh, block followed by a S block and then another W block. Here the layers are there is only one layer followed by the L+1 layer. We could have interfaced this function to take a certain number of layers as we did for the 1-qubit model, but they did not do it here. And then again, you sample random weight and you plot what that gives you, something of this form. This time, as you can see, it's not only a sine function, it's of greater order than that. And if you come to train the model, again, you take the cost, which uses the square laws that we defined up there. And then you take again the Adam optimizer with a certain batch size, and you iterate to train your model and minimize the cost function. If we look at the prediction, we have something that looks a bit like this. We were able to fit the sine function, but not perfectly. Of course, you could train the model more, and I think you still have some leverage to fit the function better. Oops, sorry. And if we actually plot the cost function, it looks something like this. So it's also converging to 0, but it's not as close as earlier. So that's basically the idea for this. And on the part 3, they're talking about sampling Fourier coefficients. We're not going to look into this part especially, but basically what they're doing is creating again a quantum model, which this time uses the basic entangler layers instead of the other one that we use. That's another ansatz that is available in PennyLane that templates. And again, they create their model with only one layer plus the last one. And they define a function here that samples different random weights. And then they do here an iteration through actually to find the Fourier coefficients that are associated with this model. Again, if you're not familiar with that, that's okay. But the idea is that we have a certain expressibility and we are able to create a distribution that is different depending on how the model is and the degree of that we set earlier. So you could look more into that if you want. And then last, here they talk about continuous variable model. We're not going to talk about that because this is not what we use in our case. We don't use continuous variable model. We don't have access to the architecture to use this model. So what we could look into here is how to turn this notebook that we looked into from the PennyLane library to the Qiskit library. So as I said earlier, we're using Qiskit in our case, and it would be more interesting to have this notebook in Qiskit. So it could be a fun, little homework that we could do for next presentation in order to be able to be more familiar with using Qiskit. Yeah. So here, the code stays basically the same. If we wanted to put it in Qiskit, that stays a square function. It's not depending on any QML library. But these two lines right here, we wouldn't need anymore. And we're not doing it right now. We're only talking about it, and then you could do it on your own later. The block stays the same. So we want to create a quantum model that looks like this, but this time with Qiskit. So the target function stays the same. We're using NumPy here, which doesn't change basically. So plotting it would stay the same. And here is the part that changes. So if we look into QML device, as we looked earlier, it produces an instance that we actually use to run our quantum nodes. In the case of Qiskit, it doesn't work exactly like this. So if we wanted here to create a S block, what we would look into is quantum circuits, which is a class in Qiskit. I'm gonna quantum circuit Qiskit here. So this right here. And this is basically to create a new circuit. And if we look a bit downstairs, we have an example here. We import the quantum circuit. We decide how many qubits there are, so quantum registers here. And this is classical registers. Basically, here we measure 2 times and we keep 2 bits of classical information. That's why we have a 2 here. In our case, it's not really 2. Well, you know, you need to adapt it depending on your circuit. And then if you see here, we do QC, which is our quantum circuits, that H, 0. What this does is basically at qubit 0, add a Hadamard gates, and that's how you write it. Next, we have a QC-CX. This time we have 2 parameters, 0 and 1. That's to define the control qubit and the target qubit. So here, as you can see, Q0 is the control qubit and Q1 is the target qubit, which we see then a CX gate, a C0 gate, right here applied, with this as a control and this as a target. And then we create here measures. We create 2 measures basically on qubit 0 and qubit 1, which we're going to write on the quantum register here C at position 0 and position 1. Then we follow by a QC.draw, which gives us this result. So in this case of our SX block here, we apply our RX gate. So instead of QC.H, it would be QC.RX. And if you want to have more information on all the documentation of the gates, I could link you this page right here. Or is it actually, it's this page right here, which is a summary of quantum operation if you want to have everything on one page. And if we go down a little bit, we can see all the single quantum qubit states. So it doubles down as a documentation, so you could read that and it would be helpful, I think, to remind you of some notions. And then here we have an example of a U gates, which looks a bit like this, and a 3-parameter U gate, which would look a bit like this. And here we have an example on how to apply said U gates. So QC.U with the 3 parameters, followed by the qubit where you want to apply the U gates to, here qubit 0. And then later down here, you have other gates. You can see the matrix form here. So basically, for example, the identity gate would look like this. This is not really useful since the identity gate doesn't do much. But you have the X gate here, which is applied this way. And then you have the Y gate, again, same thing. The Z gate, some other gates, for example, the H gates, as we saw earlier. And then if I go down a little bit, I should be able, yeah. So rotation gates are right here. As I said, Rx would look a little bit like this. So you apply a Rx gate, which is a X rotation with a matrix form looking like this. The thing is, it's not always, here with Penny Lane, they apply QML.Rx. When you transform it into Qiskit, I suggest you actually look into, how the Rx gates is implemented for Qiskit, and then a little search with QML Rx Penny Lane would bring us to the documentation for the Rx gate of Penny Lane, so that we could compare the matrix form of the two gates and make sure we have the same thing. So here it's an X rotation, so we clearly have the same thing, but in the case of the trainable circuit block where they use a ROT gate and you're not necessarily sure what this does, I suggest you actually Google it, Penny Lane, and then this brings you to the actual form of the gate. So when they say R gate, as we saw earlier, it's RZ, RY, and RZ. And you could actually either apply a rotation gate, a U gate in Qiskit, as we saw 2 seconds ago, or you apply a RZ gate or Y gate, and then followed by RZ gate. Um, so that would be a good practice to actually look into the matrix form, just to make sure that you compare the same things and you have the same gates. Because it could work in the end if it's not exactly the same gate, but if you want to actually have the exact same data, you should compare the gates and make sure that they're the same. So that's how you would do it for QML RX and then the trainable circuit block QML rotation. So you could define two different circuits, one for SX, one for W theta. And then when defining your quantum model, you could what we call append circuits together. So you could add the circuits one after the other, because basically that's what we're doing right here. Or you could directly create your circuit fully with W and S at the same time. That's up to you. You decide how you want to code it. There are multiple ways to arrive to the same result. And then here you have QML expectation value. This is not the same in Qiskit. Getting the expectation values is a bit different. For example, here when we see these two lines right here, we can get a backend, which is uh, basically where you're gonna run your circuit. Transpiling here, what it does is taking your quantum circuit QC and simplifying it. So, for example, if you have two X gate following each other, well, they cancel out. And when you transpile, you do those kind of operations. And then running here is going to be able to give you some results. And from results, depending on your backend, you get the information that you're interested in. So that's a bit that would necessitate a bit more work to go from one to the other. So for the rest, it's mostly the same. You you use your serial quantum model, you get your expectation values, you plot how it looks like, and would probably, well, actually, it would be a great idea to verify if it looks like this. That's a great sign that you successfully created the right quantum model. And then later on, yeah, as we saw here, they use QML.draw. As you could have noticed, we actually use that draw too in Qiskit with your quantum circuit. It gives something that is a bit more user-friendly because, well, I find it a lot more easier to read. Um, so you could see if your quantum model gives the same thing. And then for the optimizer and stuff, you could look into Qiskit tutorials for that. I think if I Google Qiskit QML tutorial, I should be able. Yeah. So right here, they in this tutorial you have something you know looking like this, but you could adapt it to what we have, and then later you find some code to actually train and run your model. So as you can see here, they create the quantum circuits. Um, this is a great example of how the draw function is easier to read. Here is not the same ansatz that we have for the Penny Lane notebook, but if we were to print out the ansatz here, we would be able to see it a lot better. So yeah, I suggest you look into this so that you can see how to transform this part of the code into Qiskit code. And then if we actually accelerate a little, because this mostly stays the same, and we go into the 2 qubits, well, multiple qubits circuits, the idea is basically the same. But what I wanted to show you is that the ansatz that they're using here, for example, strongly entangling layers, exist in Qiskit. Not sure they have the same name, but we can look into that. Yeah, okay. In Qiskit, the strongly entangling layers is called tool local. I think this is drawn. Yeah, so we have the. It's not the exact same thing, I think, because we have, if I'm not mistaken, in the penny lane, we have, yeah, another layer here, which is connecting the last qubit to the first one, which we don't have here, but we have another sets of ansatz that you could use, which should be the same as the penny lane one, but not with the same name. So what you look for here is actually circuit library. So I could put that the link in the chat. And then in the circuit library downstairs here, you have all the different gates, and we have here the operation. You have the generals gates, and a bit later you have research to local. Okay, you have here n local circuits, which are multiple ansatz that you could use. For example, efficient SU2. I'm not sure, but I think it's the same one. No, it's not again. But those are ansatz you could try when you implement your own uh, notebook. All right. So that's the strong entangling layers part. So here, instead of strong entangling layers, we would have, for example, two local or efficient SU2. And the rest again stays basically the same, and that's how we would pass from the penny lane to Qiskit. I really do suggest you do that. I think it's the best way to uh, get familiar with all those concepts, but also the code. It would you know start you off with coding your own QML circuits. So I suggest you do that. And we could actually talk about that next week, and it could be the subject of our presentation. If anybody wants to present their code, that would be fun. And of course, if you have any questions in the meantime, I'm available, or I think Marco is available too. But for me, I think it's what I wanted to talk to you about today. Marco, do you have anything to add?
Not really, but yeah. So
We can't hear you.
only
I don't know if.
hello, hello.
Yes, we're hearing you, Marco.
Yeah? Okay. Okay. Yeah, no, but I think we can probably start having more interaction from you guys. So I don't know if there's a volunteer for the next time. Preferably not a professor.
I can't hear. I don't know if you're speaking. I don't think. Okay, try and talk.
Hello?
Yeah, okay, great. Yeah.
Yeah, I was asking them for a volunteer for next time.
Ah, yeah. Of
Maybe
course, it's
maybe
Yeah?
not next time, but the one after that.
Yeah, it could be that.
I could volunteer for the next one if you want. In 2 weeks, right?
Yeah, it's as you want. So if you need more, you can tell us.
I can pass after Samuel, like there. So in a month.
But I would focus mainly on applications in geomatics.
Fun for me.
So probably one of the recent papers that came out, and try to understand it.
You can ask me some question if you want.
Yeah.
We were thinking more of like since you see this code in Penny Lane, maybe one of you can try to put it on Qiskit and make it work, so that you have more like hands-on experience with Qiskit.
Yeah, I have to find the time to use it. Yeah, it's a good. I think you need to try it. Yeah, for sure.
Yeah, it doesn't have to actually be, perfect and working and everything. It could just be what you tried and what you have problem with. It's I think Marco, you agree?
Yeah.
Okay.
Yeah, I mean, you can try it out and present what you have, and we'll give you some feedback.
Mm-hmm. Yeah.
Okay.
Perfect. So would that be do we look into a paper too for next time, or are we good with the code and the adaptation?
I think both aspects are important.
Yeah.
For sure, if you have a notebook related to a paper, that's the best. I think it's the case here because you have a paper, because you have the background on the paper and the application with the notebook. So that's the best combination. But it's not always the case.
No.
So, yeah, I think if we can try to find papers that comes with notebooks, that would be the best configuration, I think, for us.
Actually, if you allow me, there's a paper I will recommend for Shao. So it's the one that uses neural nets to transform data to put it then into a quantum circuit. So since I know you have some more experience with neural nets, so you can try that one. I think, let me look for it.
Can you send me by email, please? Because I don't have access to the chat since I use like an external mail address that is not the university.
Yes.
Thanks.
Let me look for the paper. Yes, this one. Okay. I don't know if I have your email.
It's supposed to be like in the envoy, but basically it's my name and like Charles.ota
okay.
at the Rainer can
I will transfer you his email, Marco, after
yes,
after the
please.
session. Like it's gonna be easier.
Okay. Okay, good. So if I get it right, so next time Samuel will present what he did, trying to convert this to Qiskit. And in 1 month, Shal will talk about quantum embeddings for machine learning.
Perfect.
Good. So are there any more questions, comments, complaints?
That's
Not
for me.
enough time. Not enough time.
Never enough time. Everything goes so fast.
Yeah. Thank you for the presentation. That was really good.
Yes, thanks, Tanya.
I hope I didn't go too fast. And I didn't see the time not going.
It's okay. They'll have the recording.
Okay.
Yeah.
Yeah.
We're gonna pass it on slow motion.
Yes. Okay. So if that's it, I guess we'll see each other in 2 weeks.
Yep.
Okay.
Good.
Cool.
See you next time.
Perfect.
Thank you.
See you.
Bye.
Bye.
Thank you very much,
Bye-bye.
Tanya and Marco.
Bye.
Thank you. Have a good day. Bye.